I welcome you again to this class. Let's solve few more problems on the kinematics of rigid bodies in relative frames of reference. Let's solve the problem 16.133. The question says, water leaves the impeller of a centrifugal pump with a velocity of 25 meter per second and an acceleration of 30 meter per second square, both measured relative to the impeller along the blade line A, B. Determine the velocity and acceleration of the water particle as at A as it leaves the impeller at the instant shown. The impeller rotates with an angular velocity of 15 radian per second. So the question is like, we have an impeller. As far as the impeller is concerned, the function of the impeller is to rotate. Impeller undergoes the rotational motion. Okay, it undergoes the rotation. Since this is a centrifugal pump, okay, so this impeller along with its blades is connected to a motor, and the motor is driven with electricity. So this impeller rotates. As this impeller rotates, it imparts energy to the fluid, and that energized fluid is given an additional head, and it's lifted. The water is lifted to different heights. For example, we use the pumps in our day-to-day life, the pump which we use in our household, what you call as a motor. It's not a motor, it's actually the pump, which is used for lifting water from the ground, okay, to the water tanks which are on our second floor or third floor, or on the roofs of our houses. In order to lift water to those water tanks, we make use of these pumps. Now, as far as this blade is concerned, this impeller is concerned, this impeller is undergoing rotation, and the notion of its rotation is it's rotating clockwise with an angular velocity of 15 radian per second. Now, what is happening as this impeller is rotating, within its blades, there is water, okay? And this water leaves the blades in the direction of AB, and it leaves with a velocity of 25 meter per second and 30 acceleration of 30 meter per second square. That is, we are having water and water is leaving the blades. That is, velocity of water with respect to impeller is equal to 25 meter per second, and we are given, this is, since it's said both measured relative to the impeller. So the acceleration of water with respect to the impeller is equal to 30 meter per second square. That's equal to 30, okay, 30 meter per second square. This is what is given to us, acceleration. So what it says, we have to find velocity of water with respect to ground, and we have to find acceleration of water with respect to ground. These two things we have to obtain. We are given velocity of water with respect to impeller, acceleration of water with respect to impeller. We have to find velocity of water with respect to ground and acceleration of water with respect to ground. So how we will do it? First of all, as we have been saying, the first and foremost step is drawing the frames of reference. So first of all, we should draw our frames of reference. The frame of reference, let's take this to be our origin. And we say, as we take this to be our origin, let's suppose this is our x-axis. We take this to be our x-axis. We take this to be our y-axis. And we take this to be our z-axis, okay? Let this to be our z-axis. So now, as far as the water is concerned, the water is leaving the impeller, okay? The water is leaving the impeller at point A, and water is leaving in the direction of AB as given to us, okay? So what we have to select the two frames of reference. So let's say this is origin O. So we have, let's suppose this is O is the origin of our ground frame of reference, okay, as well as the origin of our impeller frame of reference, okay. There is the ground and the impeller have the same centers, though you can select your ground frame of reference to be here as well, no problem at all, okay. We can select, let this to be our ground frame of reference and let this to be our rotating frame of reference, though we are free enough to do it. But to make things easy, what we do, we usually select the ground, and the ground as well as the rotating frame of reference is selected at the same origin. So we say let O be the origin of our ground as well as the rotating frame of reference. Okay, so what we are doing, we have to find velocity of water as it leaves point A with respect to the ground. So let's first of all write down now the expression for the velocity. We know we have water. Water is under investigation of two frames of reference, impeller frame of reference and the ground frame of reference. Okay, so we will write velocity of water with respect to ground is equal to velocity of water with respect to impeller, plus velocity of we write v o dash with respect to ground, that is velocity of impeller frame of reference with respect to the ground frame of reference. Okay, this is what we write, and plus angular velocity of the impeller frame of reference with respect to ground frame of reference, its cross product with the radius vector drawn from the ground frame of reference, to the point which is under observation, that is we are measuring velocity at point A, so it will be O to A. Okay, it will be from O to A. This is our velocity equation. I will again repeat that as far as the expressions are concerned, we know this is velocity of water with respect to impeller, this is velocity of impeller with respect to ground, this is angular velocity of impeller with respect to ground, cross product with the expression that we had last time. We are writing this as r o dash p. If you recall, this r o dash p vector, it was the radius vector drawn from the moving frame of reference to the point P whose velocity was to be observed. Okay, now we have to find velocity of the water at A. So we have to find velocity of water at A. So our radius vector will become from the radius vector drawn from O to A. Our radius vector will be ROA, vector drawn from O to A, like this. Okay, so if we now start analyzing this, now that is equal to velocity of water with respect to ground becomes equal to velocity of water with respect to impeller. Now water is leaving the impeller in the direction of AB as is given to us in the question. It's leaving in the direction of AB. So and its velocity is 25 meter per second, and this velocity of 25 meter per second in the direction of AB can be resolved into two components. We can say this is cos 30 component, and this component we say this is sine 30 component. That is, we can write velocity AB whose magnitude is 25. We can write this as this is 25 cos 30. This is 25 cos 30 I cap. Okay, but since this 25 cos 30 I cap is in the direction of negative x-axis, so we'll write this as minus plus 25 sine 30 j cap plus 25 sine 30 j cap. Okay, this is the velocity. This is the velocity of B with respect to the impeller, and it's with its two components. Okay, so plus velocity of impeller with respect to ground. See what is happening to the impeller. The impeller is rotating. The person on the ground says that impeller rotates with an angular velocity of 15 radian per second. That is, it's only rotating. It does not have the translational velocity. Therefore, this component is equal to 0. Then we have plus angular velocity of the impeller with respect to ground. Angular velocity of the impeller with respect to ground is 15, and it's rotating clockwise. Okay, if we curl our fingers in the direction of this arrow, then as far as the thumb is concerned, the thumb will go in this direction. The thumb will be along negative z axis. So we'll write this as this is 15 minus k cap. This is 15 minus k cap, and its cross product with the radius vector drawn from O to A, ROA, that is its magnitude is given, it's 0.3, so it is 0.3 j cap, which is 0.3 j cap, which can be written as, which is equal to, as far as this 25 cos 30 is concerned, our 25 cos 30 is equal to, it's equal to, if we calculate it is minus 25 into cos 30 is equal to 21.65. So it will be 21.65 I cap, 21.65 I cap plus 25 sine 30, that's equal 12.5 j cap. This is 12.5 j cap. And we have 15 into 0.3 is equal to 4.5. Okay, this is equal to 4.5, and its product will be, this is k cross j. So as far as the k cross j is concerned, k cross j is equal to minus I, minus will become plus, so it will be plus 4.5, and k cross j, that is minus I, minus is plus. So our total velocity will become equal to, this is 21.65 minus 21.65 plus 4.5, that is equal to minus 17.2 I cap. Okay, this is minus 17.2 I cap plus 12.5 j cap. Okay, plus 12.5 j cap. Okay, so this is the, and the unit will be, since this is velocity, its unit is meter per second. Okay, so this is the acceleration, sorry, this is the velocity of water with respect to the ground. So water, the observer on the ground will say that the velocity of the water is leaving the impeller with this velocity. This is the velocity of water with respect to the impeller. Now what we have to calculate is the expression for the acceleration. So let's write down the expression for the acceleration. We know the acceleration expression is, we will write it, the acceleration of water with respect to ground. Okay, we'll write it as acceleration of water with respect to ground is equal to, we'll write acceleration of water with respect to ground is equal to acceleration of water with respect to the impeller, plus acceleration of impeller with respect to ground, acceleration of impeller with respect to ground, acceleration of impeller with respect to ground, plus angular acceleration of impeller with respect to ground, angular acceleration of impeller with respect to ground, alpha ij, and its cross product with r from o dash to p, that is ROA vector, cross product with ROA, and minus angular velocity of impeller with respect to ground square, multiplied by RO dash A, that is R from O to A vector, ROA vector, plus the Coriolis term, and the Coriolis term is twice angular velocity of impeller with respect to ground vector, cross product with velocity of A. We write in the actual expression, we have velocity of P with respect to B, that is, observation is velocity of water at A, so it is velocity of water at A with respect to the impeller, because our beta is impeller. Okay, the Coriolis term. So this term will become for us, that's equal to acceleration of water with respect to the impeller. It says the impeller, water is leaving the impeller with an acceleration of 30 meter per second square in the direction of AB. Again, we can write this as, this will be minus 30. This acceleration will be resolved into two components. That will be minus 30 cos of 30 I cap, minus 30 cos of 30 I cap, plus 30 sine of 30 degree J cap, minus plus sine of 30 J cap. That is the acceleration of water with respect to impeller. Plus, then we have angular acceleration, acceleration of impeller with respect to ground. Impeller is only rotating with respect to the ground, because the person on the ground says it's rotating with an angular velocity of 15 radian per second. That is, it does not have a translational acceleration. Therefore, this term is equal to 0. Again, this is angular acceleration of impeller with respect to the ground. Impeller, the person on the ground says that its angular velocity is constant. When angular velocity is constant, therefore angular acceleration is also equal to 0. Therefore, this entire term will be equal to 0. Then we are left with minus angular velocity of impeller with respect to ground, its magnitude, that is 15. So here we will write its magnitude is 15, but this is here minus, so this will be minus 15 multiplied by the radius vector drawn from O to A, that is multiplied by its magnitude is 0.3, and it's along J cap, 0.3 J cap, plus twice Angular velocity of impeller with respect to ground, that is minus 15k cap, that is minus 15k cap, and its cross product with velocity of A with respect to impeller. Velocity of A with respect to impeller is 25 cos 30 I cap minus plus 25 sin 30 j cap. That is cross product with its cross product with uh, velocity of A with respect to impeller is this much, that is minus 21.65 minus 21.65 I cap 25 sine 30, that's equal to 12.5 j cap plus 12.5 j cap. So which is equal to now we have 30 cos of 30. As far as 30 cos of 30 is concerned, let's perform these calculations. 30 multiplied by cos 30. So we have cos 30 multiplied by 30. That comes out equal to 25.9. Okay, so that is 25.9. If I can, that's equal to 25.98. So this is equal minus 25.98 I cap. Then we have plus 30 sine 30. 30 multiplied by sine of 30. That's equal to 15. So this is 15 j cap. So this is 15 j cap. Then we have minus 15 into 0.3, that is 4.5. 4.5 j cap. Then we have plus, now we have, this is 15 multiplied by 21.65, and then we have k cross I. As far as k cross I is concerned, k cross I is equal to j. So we have 15 into minus 15 into 21.65 into 2. That will be equal to, okay, so this is 15 square. Okay, so we have a little correction here. So we'll write here. So this is minus, so 15 into 15 is 225. So 15 into 15 is 225 multiplied by 0.3 is equal to 67.5. So this is minus 67.5 minus 67.5, and this is j cap. So this is j cap. Okay, 67.5 j cap. Then we have plus, so this is k cross I. K cross I is equal to j. So this will be 2 multiplied by 15 multiplied by 21.65. So this is 2 multiplied by 15 multiplied by 21.65. That's equal to 649.5. So this is 649.5, and this is k cross I, that's equal to j. Okay, that's equal to j. Then we have 2 into 15 into 12.5. Okay, and this is k cross j. K cross j is equal to minus I. Okay, and this minus I with this minus will become plus. So we'll be having 2 multiplied by 15 multiplied with 12.5, that's equal to 375. So we'll write this as, this is 375, and k cross j is equal to minus I, and minus minus will become plus I. So this is plus I. If we now add up the terms, so we have 25.98 I cap plus 375 I cap. So we'll say this is equal to 349. So this is 349. This is 349.02 I cap. So 349.02 I cap. Then we have acceleration along j caps are to be equal. This is 15 plus 649.5. So 649.5 plus 15 minus 67.5 is equal to 597. So this is equal plus 597 j cap. Okay, so this is the final expression for our acceleration. So we'll write this as, this is acceleration of water with respect to the ground. So these are very, very important terms, that we are successful in calculating the velocity of water with respect to ground and acceleration of water with respect to ground. Okay, So this much you should be able to do, and in the next class we'll take few more problems. Thank you very much.